infinity of 3 over x squared plus 4 dx like this. Now, do you remember? Yeah. So how did you?
Use my cheat sheet from last
Yeah. Well,
Wolfram Alpha.
your cheat sheet being Wolfram Alpha. Yeah. I mean, the only thing I do when I look at, I understand. You had an actual cheat sheet. Congratulations. How about this? We're gonna have a gap of at least 3 milliseconds before people speak after another person. Okay. So ready? I love the efficiency of the communication in this class, but let's not overlap quite as much. I like to personally do things like this when I'm calculating integrals, just to clarify it a little bit. And honestly, sometimes it can mean the difference between recognizing it and not recognizing it. You're like, 3, how do I use 3 is irrelevant, right? The 3 doesn't matter. You're trying to show if that integral blows up or it goes to some finite number. So yeah, do you remember how you go about doing this? Like, if you can use that cheat sheet, but the basic idea is this almost looks like what?
X squared. 1 over x squared plus 1.
Are you with me so far? Are you with me so far? Oh no, yes.
Oh,
that's an evil laugh you got there, kid. So 3 over 4, 0 to this, 1 over, what does it turn into? X over 2 squared plus 1 dx. Now, is that almost what we want? It pretty much is, right? Do you see it right there? That right there is, what is the integral of that thing? It's 3/4 tan inverse of what? X over 2. Right? And what are we evaluating here? You're doing, and the thing is, I'm being a little sloppy here because can I just go straight to this? You have to be really careful. You're integrating it, but what are you doing? You're doing the limit as, let's say, b goes to infinity. Because can you plug in infinity into this thing? No. Can you plug in infinity? So what I've written right here, you can't really evaluate this to infinity. What you're really looking at here is this. So this right here is You have to be careful about this, okay? The way you would normally want to write it really properly, really properly, is you would say this is the limit as b goes to infinity of the integral from 0 to what? To b of 1 over what? Well, you can it doesn't matter what you keep inside here. You can say this is fine and pull the 3/4 out to here, x squared plus 1. Like, you can do that if you want to. Absolutely, but the key is you can't just place infinity into something you're evaluating in an integral. You can't plug in infinity. You can go to it. You can't plug it in. Even though most of the time in this math class, you're functionally going to be doing the same thing, right? It kind of is a little frustrating. Like, why do I have to write it out as a limit if I can just throw it in there? It's not the correct work. It is the correct answer, but it's not the correct work, which I'm sure your prior calculus teacher wasn't so happy about if you did. So what do you end up with, though? You end up with 3/4 times the limit as b goes to infinity. And what does this evaluate to? The arctan of what? Yeah, I don't really like, arctan is better, I guess, but I like inverse tan. It's the same thing. Of what? X over 2, but you're running this from what to what? 0 to what? To b, right? So you end up with 3/4 the limit as b goes to infinity of what? Tan inverse of b over 2, right? Plus tan inverse of what? Can you do tan inverse of 0? Does tan inverse of 0 exist? Does tan inverse of 0 exist? Just yes. Everybody confidently say yes. The inverse of the tangent of what is 0? 0. It exists. Yeah, there it's 0. Right. So the real question is, what happens? So if that's 0, you have 3/4 the limit as b goes to infinity of tan inverse of b over 2. Do you remember? This is the key. Do you remember what tan inverse looks like? Use your hand. What's it look like? Right? It's a sideways, looks like cube root, right? So as this gets huge, as b goes to infinity, what does this get infinitely close to? Close. Do you remember what it is? Yeah, you have to know what the upper limit is.
2.
Do you remember? You sure? Pi over.
Oh, pi. No, you're getting this.
Hold on, wait.
Just give me 3 to the 2. It's 3 over 2, not 3 over 4, because according to chain we have times 1/2.
Did I pull it out wrong? Oh, it is.
Because according to chain we have times 1/2.
Now that you put that out front, what do you end up with? You end up with, now we can do this. You know that this is going to be equal to, so 2 is floating out there. 3 over 4 times, what did we say it was? Pi over what? 2. 2's cancel, so what do you end up with? 3 pi over 4. So here's the deal. The question, what was the question asking us? It gave you a sequence and said, did it converge or not?
Yeah, does it converge or diverge?
Does this converge or diverge? Converge. Why do we know it converges?
Inverse tangent goes to 1.
Well, yes, because the math came out. What did we end up with? We ended up with an integral by the integral test that came out to a finite answer, a finite integral. The integral tells you if it's positive, you can run it, or all of the terms. Basically, it's another way of proving that the harmonic series diverges, right? So I think I'm trying to remember the grouping it gives you, but it starts off
6, 1, 2, 4, 8.
and then 5, 6. And it's really hard to write out over and over again, I guess. Over 7. Keeps going, right? So then they give you a specific grouping, right?
Yes.
What's the first group that they give you?
1.
First is 1. And then what's the second group that they give you?
1/2.
Then they give you just the 1/2?
Yeah.
And then what's the next one?
1/3 plus
1/3 plus 1/4. And what's the next one?
1/5 to 1/8.
So 1/8? Keeps going? Okay. So what you notice, so this is 1. This is 1/2. What does this sum to? What's 1/3 plus 1/4?
7/12.
7/12, right? So then you do this one out. Did you do this one out and give the perfect improper fraction? Did anybody do it out?
No.
What is it? Say it again.
533 over 840.
533 over what? 840. So they ask you to examine this, right? So what do you now notice? This is definitely greater than 1/2. This is equal to 1/2. This is greater than 1/2. And is this greater than 1/2?
Yeah.
Yeah, this is greater than 1/2. So we have greater than 1/2, we have greater than 1/2, we have 1/2, and we have greater than 1/2. Great. So what does B ask? Why does this show that it diverges?
No, it's first now show that each group is bigger than 1/2.
Oh, okay. So then what's the next one? How many does it imply you go to?
1/9 all the way to 1/16.
1/9 all the way up to what?
1/16.
1/16. And then what do you have to show? That this is?
Greater than 1/2.
So let's just pause here for a second. If you show that each of these is going to be greater than 1/2, what have you shown?
You have shown that you can just keep adding 1/2.
You can always add 1/2, right?
Yeah.
If you can always add 1/2, then it what?
Diverges.
Diverges. So this all comes down to, can you show that each of these groups is greater than 1/2? Good. It's always the smallest, right? Do you agree that 1/16 is the smallest? Yeah. How many terms are in this one right here?
8.
There's 8 of them, right? 8 terms. All the terms except for 1 are greater than 1/16, right? You know that 8 over 16 has to be the lowest value. It can't actually greater than. If you add all these together, you know that all of these pieces but 1 are greater than 1/16. So when you add them all together, the sum here, the sum has to be greater than 8 times 1 over 16. What's 8 over 16? 1/2. How many terms are right here? 4 terms. What's the smallest one?
1/8.
The sum here has to be greater than 4 times 1/8. Well, what's that equal? 1/2. What's this equal? 1/2. So what have you now proven? You always can add 1/2 in the harmonic series. So therefore, it's never going to converge. Can you plug in infinity after you've evaluated it in? Can you plug it in? No. You can put something in and then take the limit. You need to do this because there's all these little careful rules you have to be careful of when you're doing limits. So you take this limit. Key point right here. It converges if it has a finite answer. It diverges if it blows up. How would you go about doing this integral?
B goes infinity.
Of?
1 to B. 1 over square root of.
Yeah, exactly. Now you can integrate. Can you integrate this in a pretty straightforward fashion? Sure. So this is going to be the limit as b goes to infinity of what? It's x negative 1/2, so it's 1/2, so it's a 2, right? 2x to the what?
X to the
1/2.
Yeah, x to the 1/2. And you're going from 1 to what? B. I sometimes forget the bar. Man. So what do you end up with here? Can you factor out a 2 from this thing? Yeah. What? Or did you say yes, you can? Yes. Limit as
B goes to infinity.
of
X.
b. Well, we can plug it in now. It's fine. B to the minus 1 to the 1/2. What does this go to?
Infinity.
Yeah, you have infinity. You're square rooting infinity. So it's gonna. So what do we now know about this integral right here?
It diverges.
Diverges. Nice.
We talked something about P series also.
Be careful when you're asked to do this out. The limit the limit as b goes to infinity of the integral from 0 to b of e to the negative 5x dx. Is that something you could finish?
Yes.
Sure, absolutely. So let's actually finish it. So what does it become? Limit as b goes to infinity of what? We integrate this thing. What does it become? Negative 1/5 e to the negative 5x from 0 to b, right? Is that correct? Yeah? Something like that? It's your guys' responsibility to make sure I don't make stupid mistakes too, okay? Can I factor out that negative 1/5? Limit as b goes to infinity of e to the negative 5b minus what? 1? Right? So what happens to this? What does that go to? 0. So what does this answer go to? Goes to 1/5. Because it's going to be minus 1 times this negative 1/5 on the outside. Why did that negative 1/5 get tacked on right here? Because yeah?
The chain rule.
Yeah, because of the chain rule. This is kind of what we were getting to, what James was alluding to. Convergence and divergence of p-series right here. So this is a p-series because it's 1 over x to the p-series. So the question is, determine for which values of p the improper integral diverges and when does it converge, okay? So here's part of it. We already know the answer to this. We know it converges when what? When p is, when it converges when p is less than 1 or greater than 1?
Greater than 1.
Greater than 1. You have to be careful because it's in the denominator, right? So how do you prove this? Well, you can do it in cases by setting up exactly what we set up so already. So if I just gave you this and we worked on this just like we did the other two, what would we state? We'd state the limit as b goes to infinity of the integral from 1 to what? B of 1 over x to the p power dx. Yeah, there's a lot of variables. That's what we'd have to evaluate. P is a constant, though. Can you anti-differentiate that for me? Well, I'll rewrite it for you. That's the same thing as the limit as b goes to infinity of 1 to b of x to the negative p dx. Are you with me so far? And what are we evaluating this from and to? 1 to what?
1 to b.
1 to b. Okay, and what is b doing? B is going huge, right? It's going big. Okay, so now we get to do a visual analysis here. Really don't. So what do we end up with? The limit as b goes to infinity of b to the p plus 1 times 1 over negative p plus 1 minus what? Okay, hold on 1 sec. I have to fix something. There you go. So then what are we subtracting from this? We're plugging in 1, right?
Just 1.
1 to the, don't convert it yet, just do this. P plus 1 times what? 1 over negative p plus 1. So we can kind of eliminate some of this from consideration because it's not that important. This right here, what is that going to equal?
1.
That's just 1, right? So if we actually simplify this there, negative p is going to be less than what? Negative 1. So what does that mean? P is greater than 1. That's where that comes from because everything else doesn't really matter, right? For convergence or divergence. The only thing that matters is this thing right here. You want it to blow up or go to some finite number. And you know it's going to blow up because this is going to go to 0 if p is greater than 1. That's where it comes from. If you want the super proper, like all notarized, saying you have the first quadrant here, and let's say you're going all the way to 1. So let's just call, I'm not using the right scale here, but let's say it's 1, 1. But what is this thing going to look like? Yeah, you can get over it. It looks like this, right? You're trying to add all that up all the way to there. The problem is, can you ever actually evaluate that function at 0?
No.
What your math professors in college will expect? You know this is true. If n is greater than 0, right? N cubed is less than n cubed plus 1. What does that mean? It means that 1 over n cubed plus 1 is less than 1 over
N cubed.
You know that n going from 1 to infinity of 1 over n cubed, it converges, why? P series, and p is greater than 1 because p is equal to 3. You know also that this, so because Pause it right here. I'm trying to do it in the right order. One out as a group. You don't have to do this stuff. So let's look at the one on the left first. It says use the limit comparison test to determine if the following series converge or diverge. Okay. So on this one right here, we'll call it. Let's just call this one an. So what we're looking for, we'd love to find a bn, so that when we took the limit as n goes to infinity, we ended up with some constant. So if this is an right here, does anybody have a guess as to what they think bn should be? Yeah, hold on. So it's going to be the limit as n goes to infinity of what? N to the fourth plus 6n squared all over n to the fourth minus 2n plus
3.
And what do we know that equals by our powerful knowledge of limits?
1.
1. Therefore, what do we know about this? It converges. Yay! Good job. So if this is an, you know what I'm going to do? So if this is an, there's a really cheap trick. I'm going to call bn. Anybody want to guess? No. It's a cheap trick, okay? It's kind of a cheap trick. So what are we looking at? We're looking at the limit as n goes to infinity of sine of 1 over n over what? 1 over n. Is that correct?
Yeah.
How? But but careful. How do we go about doing this? How do you just know?
We just know.
How do you know? This is the same as what?
This is 0. This is going to be 1.
The limit as this is the same as, let's say x goes to 0 of. Yes. It is the limit as x goes to 0 sine x over x, which is 1. This is a cheap trick, everybody. Cheap trick. It's essentially like it's a substitution. It's a cheap trick because n going to infinity of 1 over n is the same thing as x going to 0 of x. So you just rewrite. Oh, look at that. It's 1. So therefore, what does it have to do? It diverges or converges? It converges.
The class before is just perfect.
Pretty cool, huh?
The class.
Wait. Bn diverges.
Bn diverges? As n goes to infinity?
I mean, Bn goes to...
If one diverges, the other one has to. Thank you for the guy. No, it's fine. It's fine. It's okay.